Right.
So it's really trying to get our clients to see that we need to get really everybody involved. When you have to improve something, you need maintenance involved, operations, engineering, somebody with the eye of the particles. So we care about the particles. Particles matter, and we need to make sure that they can flow.
Hello, welcome to Mining Now. I'm your host, Jerrod Downey, and today we have Jenike and Johanson on the show. I believe it's first time
Yes.
being on Mining Now, so very excited to have you. We're filming from Salt Lake City, put on at Mining Exchange, put on by SME. Very excited. Thank you for being on the show. I'm going to make some introductions here. Tracy Holmes, President. David Craig, Vice President, and Carrie Hartford, Director of Business Development.
Yes. Thank you for having us.
It's going to be a lot of fun. We got lots of notes to cover, so we're going to get into it. Tracy, I feel like you're the president. You should probably introduce the company. I always just assume nobody knows who you are, even though a lot of people do. But who's the company, that bird's eye view?
So I think I like to say that we're a boutique consulting engineering company.
Wait, you have offices in?
Boutique's a loose word.
Yes, I like to use the word boutique because it sort of distinguishes us a little bit from just regular consulting engineering, I guess. We're specialized in the area of bulk solids handling. We're a global company. 7 offices across 5 countries, and specialized in the bulk solids handling area. That means it covers a lot of different industries, from mining, I guess, is the biggest one, but glass manufacturing, cement manufacturing, food, pharma, plastics. Basically anyone who's handling large collection of particles.
Right.
That can be in the mining. That would be from ore all the way through the screening into the chemical processes, feeding it into the processes, collecting it out of the processes, feeding into the next one. So lots of different materials, lots of different characteristics. So we look at the characteristics and we help to design the bulk material handling equipment to help make choices about those things, and highest level consulting engineering, but doing a lot of testing to support the sort of science of bulk material handling.
Is it these different sectors? Are mining engineers working on the glass bulk handling? Is it cross discipline?
Usually not. I would say that the physics of bulk material handling fits in all of these kind of different categories. So we're applying sort of the main bulk material handling rules to the different industries, depending, and they may have different focus things going on. So like mining, the focus is all about throughput. In pharma, for example, the focus is more on content uniformity and making sure that their product is exactly the same every single time.
Right.
And sort of variations being
So there's different disciplines that apply more to that.
And I would say, in our different offices, we have offices in Australia, Brazil, Chile, and Canada. And then within the United States, the headquarters is in Massachusetts, which is where David's at. And we have an office in California where I'm at, and an office in Texas. Within the United States, we have such a broad range of industries. So our engineers, I'll get in one phone call in one day, pet food call, a pharma call, a chemical call, and a mining call. And that would be a very typical day.
Is mining up there with the more challenging ones, especially when you say terms like boutique, because minings are so unique?
I think what's unique about mining is that bulk materials handling flow is the majority of what miners do. You find it, the geologist finds it, you have to get it out of the ground, you have to transport it, you crush it, you size it, you get it through all this process. The entire thing is bulk materials handling. And if material doesn't flow, then they're not making money. They're not hitting their throughputs. And we really want our clients to succeed. So that's what's unique about mining, is it encompasses the entire part of their process.
Right.
That's really, I guess, fundamentally who we are as a company. that the company was really founded in 1966 with the idea of providing reliable flow of bulk materials. So we have come up with ideas to actually measure the characteristics of a material, and then we came up with numerical models, mathematical models, to predict how material will flow. And we've applied that over many years now in terms of designing equipment. And I guess with regard to the mining industry, so we can design silos and bins and hoppers and feeders with predominant transfer chutes, with predominantly the idea of using gravity to get the material to flow reliably through the process. And as I guess was mentioned, so obviously the mine wants to kind of do X number of 1,000 tons an hour. How do you maintain that as the maximum level of throughput? And that's where we come in. So we design the equipment so it doesn't plug in the bin, it doesn't plug in the transfer chute. It allows the material to flow through very readily. It doesn't wear the equipment. So that's really our kind of niche market, as Tracy was saying in the beginning, that we're there as a company that we could engineer these processes to get the material to flow reliably from point A to point B. And that's where we're kind of supporting the mining industry in particular.
How much of the work is from operations that they have a challenge, as opposed to it's a new project, you kind of get to start from scratch for your own design?
I think most of our work comes I think we just recently had a meeting where we kind of reviewed a lot of this. The biggest proportion, I would say, is people who've used us before and liked what we did. And a lot of that comes from they had a problem and then reached out to us and found us and, you know, asked us to help in sort of an emergency kind of thing. And we do get a lot of new traffic that way as well.
I think about 60%, give or take, every year is in retrofit type. Somebody has a problem, they come to us, here's our problem, can you engineer a solution to help us? Obviously, we kind of like that work too, but we also like the work in terms of, okay, it's greenfield, we haven't done this before, we want to do it the right way first time.
Right.
And that's really where we like the industry to get to. So we're not just trying to troubleshoot existing problems, but we're really helping the industry kind of move forward with the technology that's out there.
Yes, it's mixed emotions every time we get one, right? Because it's like sad that that's happening again. And also good because we're given the opportunity to help.
Well, that was actually my next question. Are there, when that phone rings or that email comes through, are there a few, specifically in mining, that they're the common, there's the bottlenecks that are happening?
Yeah. I mean, I've picked up the phone like on a particular day and been asked to be at their mine site in the middle of nowhere, Canada, by tomorrow. And like, you know, our stockpile is, there's a rat hole and it's not flowing, and my boss said, get someone here right now.
Right.
So
are there common spots where are there common ones, you know, like it's the most common place where that happens?
I'd say for mining, it's usually a no flow situation. So that means a rat hole in a stockpile or a chute
What's a rat
plugged. Oh, a rat hole is, you take it.
Yes.
Oh, is that what this is right here?
Yeah.
Great question.
Wow. I honestly didn't know that.
Well done, Jerrod. So yeah, transfer chutes is a big one for us. So plugging of transfer chutes, wear through transfer chutes is just not flowing reliably, spillage onto the receiving belt, bins, feeders, stockpiles. So, you know, the default flow pattern of materials emptying out of a bin is where it just funnels in on itself.
Yeah.
But the problem is the rat hole can occur. So it looks like a rat ate its way down. So there's a hole going all the way down. So if you look from the bottom, which is not safe in production, don't do that.
Okay, but here we can.
But here we can. And so here comes the sledgehammer or the operator intervention.
Yes.
Yeah, you get to play.
All right.
So at the end of the day, it's not a very reliable flow pattern because it just doesn't come out. But you think, and imagine this in a really large scale when that rat hole collapses.
No one's ever tried to invent something that does that, I hope.
Yeah, and I think
there's
a few spots out there. So that's what we call funnel flow. It's funneling in on itself.
Right.
Now the other side is what's called mass flow. So all the material is in motion as it flows through the outlet. So now particles are moving along that wall. There's no more stagnant material. By definition, no more rat holes.
Right.
So whatever you put in first comes out first. And whereas funnel flow, whatever you put in first, well, you can get an arch or a bridge, just not coming out. but it stays here and it doesn't come out to the end if you're lucky that it comes
Is this
out.
and this is all because of this angle here?
Yeah.
Correct.
It's happening.
Exactly.
Yeah.
So this angle has to be steep enough and smooth enough for material to flow along that surface.
Now, does that angle change based on the material itself, or
Yes.
is there a standard that?
There's no standard, and that. So
Okay.
Dr. Jenike, what's unique about and very special about being here in Salt Lake City is at the University of Utah in the 50s and 60s, Dr. Jenike developed the whole theory of flow, how to make it flow. And so the equations he developed allows us to test material on a bench scale level and obtain data to know what this hopper angle should be, measuring the wall friction, and then cohesive strength, how big the opening needs to be to design reliably for these systems. And then Jerrod Johanson was his grad student. So this year, 60 years ago, Jenike Johanson was formed.
Really? That's
Yes.
so that was out of here.
It was out of Salt
Wow.
Lake City,
Wow.
University of Utah. So it was a really big deal when Jenike published his work. So for liquids, you have Bernoulli's equations for fluid flow. For bulk solids, you have Jenike's equations for bulk material flow of solids. And so in universities, it's not often taught. And so in our mindset, well, this just fits, and that's what fits our geometry, and that's why it was designed. But we want to design reliably for this. And this inherently, as an engineer, you're like, yes, this is what I want.
Right.
But you're not going to get there unless you have data.
Right.
It's a strong function too of the material itself, of the particle size, of the moisture content, and also of the material of construction. Because you could have, say, carbon steel, it might be rough, or ceramic, it might be rough, and you need steeper angles to get the material to flow along it. Or you might have something that's relatively low in friction, so you can make the hopper angle shallower and still get the material to flow along the wall. So, but it's a strong function of all these parameters. And what we do in our laboratories is we actually understand from the client, okay, what's the particle size, what's the material, what's the moisture content, what's the time storage at rest. We take all these things in consideration, and then we put the material into the lab. We test under those conditions, we get the results, and then we go back and do the engineering based upon those critical parameters.
Okay, you've got a couple things on the table here, though. So I've got this one now. What's that one?
Yes, this is our segregation model. It is salt and chia seeds. And what we're looking at is as material that has a difference in particle size discharges, you tend to get the fines in the middle and the coarse will
Right.
roll to the outside. So you'll see this in any stockpile, any pile of rocks
Can I get
around
that one over there?
You absolutely can play all you want. So you'll see in a stockpile, you make a pile of rocks, you can see the bigger ones on the outside of the pile. But this can have a major implication to having a bunch of fines. So let's say this is a stockpile. You have your fines in the center, the coarse on the outside. You may have the feeders on the outside work fairly well, but in the middle, because it's all the fines, that could be wet and cohesive. Then you have a lot of arching problems. If you're in a funnel flow bin where you're discharging, hopefully you can discharge through the middle, you're going to have all the fines come out first, followed by the coarse material. And this could really upset, say, your grinding system if it gets a slug of fines versus a bunch of coarse material. If this was a powdered drink mix, you would not have the right blend of, say, caffeine and flavoring and colorings and everything. So segregation can be a significant thing. You can go down a transfer chute and look at this now. Did I solve my segregation problem? I actually just created a different type of segregation. So the fines tend to go to the bottom and the coarse are on the top. And you'll see this on a conveyor belt. The coarse will ride on the top and the fines on the bottom. So there can cause some significant implications to a processing step.
And sorry, how does that? I missed how that you're fixing it in which way?
So in funnel flow, you're going to exasperate that issue, this sifting segregation.
Right.
But if you're discharging in mass flow, now you actually recombine the material, the fines, and the coarse as it comes through the outlet. So you're minimizing this side-to-side sifting effect.
Wow.
The sifting happens, but then that whole layer
Right.
comes back to the outlet together. So the fines and the coarse get remixed on
Absolutely. So it just helps people to see because they experience these in their processes and have all these issues, but you can't necessarily look inside your bin and see what's going on. So it helps as a talking tool.
Is there a project, David, that stands out for you that you go, this kind of exemplifies the value we're delivering?
Well, I guess interesting question, and Carrie was actually presenting with one of our clients yesterday at the conference here, and we got involved with the project a bit over 12, 18 months ago now, and it was a transfer chute handling copper ore, and what was happening the material goes, they crush it down from say 12-inch minus, it goes down to half-inch minus, go through an agglomerator in terms of adding moisture content into the material before it goes to a leach pad. And the design originally was such that the material flowed quite well, but then it wore quickly through the transfer chute. So they had the idea to minimize that wear to redesign the chute. So when they did the redesign of the chute, they had all sorts of plugging problems. So this customer in particular contracted us. We went out, we inspected the site, looked at the existing conditions. We got a sample of material. We put it into our laboratory, measured the characteristics. And then what we could do is actually using technology that we have, and in particular, this particular case, was discrete element method. So we actually model discrete particles and the interaction between those discrete particles and the interaction between those particles and a boundary. And then we can actually calibrate the material from our lab to the actual characteristics in our numerical model, the DEM model. And then we can actually compare it to the field. So we did that, and the material came off of the conveyor belt, went through the kind of upper area of the transfer chute, and then what happened, it had to make a very abrupt angle change. So you can imagine like momentum, you're going down like a water slide, you want to be kind of continuous change of angle, where the material in this particular case hit pretty much at 90 degrees, lost all its momentum, built up, and because of all this extra moisture content for the fine material, it was very sticky. So the material built up and quite quickly plugged the transfer chute. So then we went in with this knowledge and with our knowledge of material flow, so we could reduce that impact angle. So it was kind of very smooth, a few degree angle change, redesigned the chute, we provided engineering our solution, and then the project was implemented, and it works very effectively now. So that's something that kind of comes to mind just because of the presentation yesterday.
So why would they designed it with that angle in the first place? It's different. Is it a different?
So a lot of times it's lack of knowledge of the flow of material. And in this case, they said, well, maintenance wise, we really want to be able to come in and access the chute. And so they made some unique changes so maintenance can come in and try and unplug the chute. But that actually made it worse in terms of flow.
Right.
So it was unintentional consequences of those decisions. And we see that all the time where lack of knowledge of the theory of material flow causes you to make decisions for operational reasons, maintenance reasons, but you have to really incorporate those changes with the knowledge of flow of material.
Right.
So it's really trying to get our clients to see that we need to get really everybody involved. When you have to improve something, you need maintenance involved, operations, engineering, somebody with the eye of the particles. So we care about the particles. Particles matter, and we need to make sure that they can flow.
So we've done episodes, these companies that build like liners, they put them in trucks and chutes and things like that. If you went and like, let's say a new vendor came along and sold you on a new lining system, could that affect it? Something that simple?
Absolutely.
It's not a simple change, but.
And the beautiful part of Jenike's work is that we can test the frictional nature of the particles on that surface before you even try and install liners, which can be very, very, very expensive. So rather than trial and error approach, take a scientific approach, take a step back, test on those liners. Will it reduce the friction enough for reliable flow? If the answer is yes, then absolutely. Now you have an answer and a way to go. Maybe you add different liners and you make a little configuration change. Yeah. So we have test data to go with that.
And like, talking this through, I just something popped into my head, a situation where we had an apron feeder, and on the hopper walls leading up to that apron feeder, they had, in this particular application, it was an oil sand application, and there was a lot of wear happening on the lining surface, and to slow down the wear, they installed these like kind of like bars across the edge to like slow down the material flow on that hopper walls. And of course it worked. It stopped the flow.
It worked beautifully.
But also it stopped the flow.
Right.
And they just didn't have the rate that they wanted to get. So yeah.
Would that have been an engineered thing, or did they just like...
They just decided to try that and see what happened. And then they weren't getting their throughput rates that they wanted to get. And then they reached out to us and said, well, can you help? And we were able to help them with some changes to the interface geometry and everything to get back to a place where they had their rates. But they had the wear. They had to deal with the wear.
Right. So then you also have to deal with that then.
Yeah, and that goes back to your question of like, why might they do it? And one of the reasons Carrie gave was a lack of knowledge. And another one of the reasons in mining often tends to be that we don't want the wear, right? We want to do things to stop the wear because things are like the wear on the hopper surfaces or chute surfaces. So to save wear, they might put in a rock box, for example. But if you're not very careful about the geometry of that rock box that you're using instead, then you run the risk of having no flow under some of the circumstances that the system might face.
If the ore body changes, can that also change? So it's set
Very
up good
much.
for
Really.
3 years, and now it's a different ore body, and now it changes.
Yep. And moisture contents can change. Just
Right.
the choice of how much explosion, what's the
Yeah,
right
the
word?
explosives too.
Explosives, thank
Yeah.
you, that you put in, how they map that out, how much they use, that can
Right.
affect the particle size distribution of the
Right.
ore. Obviously, the chemical, the assay, the mineralogical properties, all those things can play a part too.
So you mentioned your lab several times. What is that? When we're talking about a lab, what are we talking about?
So what we have a series of labs. We have one in where I'm from, Massachusetts. So effectively, it's like a soil mechanics tester, effectively. So we took that technology, or Dr. Jenike and Johanson did, and we applied that to bulk solids. So where you look at soil mechanics and the pressures are very high, the material is really in situ. The bulk material, the pressures are very, very low, and then the material is flowing. So we wanted to get it to fail. And so what we've done, we've set up the lab itself actually takes typically like a 3 3/4 inch diameter cell. You put material into that. It could be 8 inch, it could be 12 inch, it could be larger. But we put material into this cell, and then we kind of shear the top of that relative to the stationary bottom cell. We can then we can get kind of more circles, we can get cohesive strength, we can get internal friction, we can get boundary friction. And then, so what we have a series of kind of designated labs. So everybody has their tester, the data acquisition information, and they go through a series of tests to generate this information. It's analyzed, and then we create what we call a flow properties test report that really summarizes all the information so an engineer can take that and use it for design. So if I have a conical outlet, a round outlet for argument's sake, what's the minimum size to prevent an arch? We need to be greater than that to get the material to flow. If I have a slot where the length of the slot is, say, 3 to 1 the width, I can look at what the width of that slot is to prevent that arch. So we've got the lab, and we routinely go through many samples, many tests, and to the point just before too. Yes, the material varies within the mine site, and then what we try to do is pick different locations within the mine, and then we can test different locations. We can test different moisture contents, different time storage at rest, and then we get an envelope, and then we can kind of design worst case. So then the equipment that's going to go in, we're kind of guaranteed, okay, this one material or one location within the mine may kind of give us, could be high clay, could be high moisture content, something of that nature. We can maybe use that for a particular design. Maybe another area is very fine and very dusty. Maybe we need to use those characteristics for, transfer chute, minimizing dusting. So we can kind of pick and choose within the actual mine where to get samples, where to test, and how to provide that information for engineering.
Kind of planning out life of mine.
Exactly.
Right, okay.
And that's actually one of the major values that I think Jenike can bring to a project, actually, is helping to build out that test program, figuring out what are the variables that are likely to matter, and then how do we cover them all off in the testing. So doing the testing, but also understanding what testing to do, what's going to become important. And to Carrie's point about particles matter, the idea that in that stage of things, at the very upfront stage, we are asking questions to tease out what are going to be those variables that will matter.
Right.
Of the people who have the information that we don't have, but aren't looking at it from the perspective of bulk solids.
And so, the things that affect flowability are usually the fines dictate flowability. So we're looking at fines, but we're going to adjust that moisture content, for rainy seasons, for dry seasons, whatever that might be. And then we apply that. And so we've actually built all our testers in our lab in California for all the other labs. So we have the lab set up, as David's saying. So it looks like a typical lab setup. That's in Australia, Brazil, Chile, Canada, and in Massachusetts. And then in California, we actually do large scale testing. So we talked about where quite a bit.
I was going to ask you, how close to real world application do you get?
Quite close. So we're trying to mimic it. And that's the whole idea, is mimic the process conditions. And we actually have a furnace to test up to 1,000 degrees C. So if our client's process involves heat, then we want to match that. If it involves freezing, we match that as well. We have environmental chambers, we have glove boxes, we have all the ways to condition the material to what would be happening in the field. And if we can't mimic it, sometimes we need to go to site and actually get samples fresh hot off the line, whether it's out of the dryer or whatever it is.
And knowing when to decide that's really important, and when to say, okay, we could, if it's very hazardous, for example, the material, we could maybe use a surrogate, or we could learn some things by using a surrogate, and then do, minimal testing or on-site testing for the actual conditions.
Because would you be piloting in California a site for Australia?
Yeah, we've done tests for them. We do the wear test. We're looking at the abrasive wear against the surface, like those different liners. We can test what that wear rate is. We do pneumatic conveying. We do large-scale testing like gas-assisted discharge, fluidization. So sometimes we've built models. An example I was thinking of, we were talking about earlier, is a client was saying, well, we have this set. We have a fairly steep bin or hopper underneath a train loadout system and a big stockpile in front of it, but we have limited live capacity. And we want to put an insert in on top of it to expand the flow. Now, to clear off an entire stockpile on a train loadout facility is a very expensive. It's no small undertaking. And so let's model this on a scale level. So we did a scaled model, physical model in California, and we were able to look at it with and without the insert, and we were able to calculate that percentage of increase of capacity, and it justified their project.
Oh, because you would have essentially had to do it twice. You would have had to go test and then go implement, right?
Yeah. So we tested on our scale. We did all material testing.
I see.
We calculated what it should, but then to just really provide more clarity and reduce project risk and see what else we can learn, we did the physical modeling. And then when they went and implemented, it really actually matched quite well.
But sorry, on that case though, what did the material change? I mean, they must have, when they built that, did it go wrong from day one, or was it 2 years later material changed? What happened? This is the president and me going, what? Who messed up? Sorry, I'm okay.
Yeah, you're okay. It's
This is where the knowledge comes into play.
I'm the person that phones you and goes, okay, we had someone, I want you to tell
something
me
messed
You're
up.
the 60% that comes to us, yes.
So there's a lot of things that can go wrong. One, maybe it did work for the material they had, but then when they go deeper into the mine, you get closer to the waterbed, you get higher moisture.
The moisture.
You get more clay. You tend to get more fines. And man, that combination of those three changes will change something that may have been working quite fine.
And then I guess even weather conditions.
Maybe they didn't maintain it well. And now it's caused a lot of mismatch maintenance, and it's not flowing well anymore.
One thing,
Maybe they're trying to get higher throughput.
Higher throughput's a big one. They never go down in throughput, let's be honest. They always go up in throughput.
Gold prices right now, they're going for it. Yeah.
One thing, I guess, we were looking at the rat hole in the bin, and this is very similar in the stockpile too. I think in terms of design, and this is to your question, is that a lot of people, and we would see this probably 99 times out of 100, in a stockpile, they don't assume it's going to form a stable rat hole. They assume all the material is going to draw down, so they get 100% kind of reclaim effectively for a free-flowing material. And very few materials are actually free-flowing. So they do want to form a stable rat hole. So we see this a lot. So where somebody in a stockpile will come up and say, okay, I've got my 3 feeders lined up like this. All the material is going to draw down to my angle of repose. I'm going to get, I don't know, 50,000 tons capacity out of this stockpile. And then they put it in day one. It's a little bit more cohesive, and they've got this stable rat hole now that opens up a very steep flow channel up to a certain point, and then it's shallow kind of expansion angle, and they might get 8,000 tons capacity, and then they call up and say, well, what happened here? It's because we have a stable rat hole, and they didn't really take that into consideration in terms of design. And this happens throughout the industry pretty much 99 times out of 100.
Well, this leads to my sorry, go ahead.
I was just going to say, that's often leads to very unsafe conditions that then they try to reinitiate flow, whether they bring in a front end loader or some kind of excavator, push material in, and dozers go into these glory holes, the rat holes every year, and people die. And it shouldn't be that way. And the reason is the initial design is incorrect for that material.
Well, brings me to the next question: is the actual OEMs, the suppliers. What is your relationship with them? How do you, if a company has already procured a supplier, what's your approach? How do you manage all that?
Can be an interesting challenge sometimes. Yeah. I think typically we tend to work for the end clients in the mining industry. That's definitely probably the best option for the project and for us. But we do work with the OEMs and we do work with the EPC companies as well. And, I think we put a lot of energy into keeping those relationships good and really trying to explain and doing things like this podcast to, get the word out there. I myself have been sort of doing it for 30 years. And 30 years ago, things were a little bit different than they are now, in terms of me traveling out to mine sites to try to tell the guy in charge there he's doing it wrong.
He says thank you. And,
Yeah.
Thank you for letting me know.
Yeah, they didn't always listen.
that's really nice of you to tell me.
Yeah.
And we're vendor agnostic. So we're not attached to any vendor. What we really want to do is get the right complete solution for the client.
Right.
And so whether we do just testing recommendations, right? First of all, you got to find out the solution. Or if it's a new application, the right design.
Yes.
But you can't just stop there. You have to then implement that well, because a lot of times changes start to get made as you go through the detailed design phase that are not the best thing for the particles. It's the best thing for maybe a piece of equipment to fit or for fabrication, but it's not the best decision for particles. So we need to stay in
schedule.
For the schedule.
Yeah.
And then all the way through. So we can go all the way through detailed design. We have a whole structural department, and we can supply custom equipment. We build equipment in our lab here in California. And there's a lot of ways we want to make sure the right solution gets implemented, and whatever that looks like.
Yeah.
David, you look like you were going to jump in there.
Oh, I was for a second. And we have examples of this, and we kind of see it all the time. And I guess to Carrie's point too, we like to stay involved in the project as much as possible because changes have been made and continue to be made. So we'll come up with a basic concept, or we'll do detail engineering, and invariably somebody will change it. And it was even the transfer chute project we were talking about, and it makes sense. Like you could buy, I don't know, typical 12 by 12 inch tiles, ceramic tiles, or 6 by 12 or something of that nature. And so everybody would want to put in standard size tile, and can't blame them. But if that affects the flow performance, and you don't get reliable flow, then that's a problem. And kind of one example came to mind. We had back-to-back projects here recently. And in one particular case, we did the site visit initially, understood the problem. We did testing, we did conceptual engineering, detail engineering, we did equipment supply, and then we were on site during installation. And it started up at 100% nameplate capacity day one. The other one, we went through site visit, we went through testing, conceptual engineering, detail engineering, until what Carrie was just saying. Then somebody took fabrication, and then they changed things, and it kind of made sense to change. Okay, we can't get that shaft size, we have to go different. We can't get those like screw flights, we have to go different. We can't, we don't want to offset. We see a lot of this in bin design. The lower section would form an upward facing ledge, so the material gets hung up on that ledge. We see that for whatever reason in terms of fabrication. So that one didn't start up day one and had all sorts of problems. And even today, it won't meet nameplate capacity. So when you're spending all this money and time and effort to get something to work, and then again, it comes back to knowledge, I guess, because the fabricator typically is not going to realize, okay, the intent of this is to not have an upward facing ledge. The intent of this is to get the material to hit at this angle. And yes, you can change it, but you kind of lose that intent as you go through the project. So I think the more people can work together in terms of, say, our group, in terms of the EPC or the OEM or the fabricator or the installation crew, the more people can work together, I think the better solution is for the overall, the end customer. And that's what we're trying to do. So we don't necessarily have to do everything as part of the project, but if we're involved and we're talking to people and then everybody's talking as part of this kind of project, it does seem to go a lot more smoothly in terms of the that flowability of the material through the process.
Tracy, I've got to ask you, when you talked about, 30 years ago going on site and telling people what they need to do, what did you learn though? And let's say those first 10 years of that experience, I mean, that experience must still dictate how you as a company and culturally approach change management, essentially, is what you're asking.
Yeah, I mean, I don't know. Things have changed a decent amount in my career looking at things. I don't know. So my dad is a mineral processing engineer.
Okay.
So I grew up mining. I don't know. They talk about military brats. I like to say I'm a mining brat.
Right.
Lots of different small communities kind of moving around. So I kind of already, coming into my career, I already knew what that was like.
Mm-hmm.
So I think I was a very good candidate for being what's the right word? The person who goes out and helps get the word out.
I know what you're saying.
I can't
now.
think of the word. Anyway,
Yeah.
The advocate or
yeah, an advocate, anyway, to go out and kind of get the word out. And because I kind of, lived that life and sort of belonged to that set of people, if that makes
Right.
sense, and was part of the fabric of the culture. And also because I think I'm very I'm enthusiastic about bulk solids handling. Like I discovered Jenike and Johanson in my third year co-op, one of my co-op terms. And
okay.
I was working structural co-op, and I was given the job of sizing a bolt for an insert that Jenike and Johanson had designed. And I had no idea where to start, right? But I thought, I'm going to call Jenike and Johanson, and I ended up talking to the guy who then later became my boss, and to ask for help. And he said, yeah, oh, you're a student, I'll help you. He sort of gave me homework. I sort of did the homework and then reported back in, and we kind of worked through this problem together and then ended up with a bolt size, and they ordered it. And through that process, I decided I want to go work for Jenike and Johanson. So I had this, I thought, that's a great company, and
Because of
I
the
want
company
to
or because of that individual? Or
both.
Both.
Like because of the subject matter, because of the potential impact that that we could have. There's so much need, basically. Like I said, I stood there and I was like, okay, I have to size the bolt. How do I do that? I have no idea, right? And that's not something you're taught in engineering school. Nobody teaches that, really. I mean, there's a few, but it's very limited. And my feeling is, and my strong feeling is, that every engineer in Canada, and probably a lot in the US and most of the world, ought to be learning about bulk solids handling in school, to go out into the world and become engineers using the science, understanding that there is a science there, understanding that it's a tool that they can leverage.
So that's a very limited. There's very limited education.
Yeah.
there is. And
Yeah.
I'm a mechanical engineer, and I think I had one day on soils mechanics. Hardly understood it. And then I went and worked for an oil and gas company, all liquids, all gases. And then through a series of circumstances and moving to a new location, Jenike was hiring. I'm like, what is this bulk solid thing? What's a hopper? But once they did the model,
Yeah.
my mind was like, I get this.
Yeah.
And this is something I would love to help people overcome problems. Like, I love helping people. And I think everyone in our company actually really enjoy helping people
I think so too.
do something better. And we tend to retain our engineers for a very long time. Just at this table, you have just under 90 years
Really?
of material handling experience at Jenike and Johanson,
Wow.
just right here. So
Well,
we
we don't
dye
look that old, do we? Really?
we dye our hair well.
I was like, am I supposed to give a comment?
You were supposed to compliment. That
I
is
could
it,
get in trouble.
I just avoid making any comments about. I just sit and listen when people start
Nope.
talking age, experience. I just go,
I'm not biting.
That's probably now
Not
why.
biting. Yeah.
It's interesting, though, in terms of, I guess, the history and joining the company and not knowing about bulk materials handling. And I'm from Australia, so I was born and raised there. And then we actually had coursework at the university in bulk materials handling. But the irony is to this is that my professor, Alan Roberts, in the University of Newcastle in Australia, he was across in the US. And he, at that time, this is back in the 60s, 70s, I forget exactly the time, they could invite somebody in once a week to actually talk at the university. So he knew of Dr. Jenike, he invited him in there and kind of wasn't involved in bulk solids handling at all, struck up a relationship, took one of his testers back to Australia, set up bulk solids in Australia, and here I come along like 20 years later and can do coursework and learn about it. And then I stayed on at the university and kind of was trained and was working. And then I had the opportunity to come across and work for Jenike Johanson. But
I didn't know that, David.
it's kind of it's very interesting. And the funny thing was, it's purely
This is why they pay me to do interviews.
Yeah.
Yes, exactly. And it's purely because I was out mowing the lawn, and the old dean of engineering lived 2 doors down from me. One thing led to another. We had to do 12 weeks work experience to get a degree in Australia, and then I went across to work for the group, and
Wow.
led to another. So it's interesting. But the funny thing is, and kind of the sad thing at the same time, it took somebody from the US and Australia, the person from Australia visiting here, to take the information back to Australia to set up and then to push that technology. In the US, it's kind of died out. It really wasn't taken up by the universities. And I think it's very important because we always come back, or we've been mentioned it multiple times, knowledge. And if people had the knowledge, people would be in a lot better situation in terms of plant design, operation, maintenance, and really get the throughput that they really want. And I think that's probably what we're trying to do, because our company, okay, is going to be 60 years of age in August of this year. But we would like to really be as well known as the Navier-Stokes equation, et cetera, in fluids, like really have the technology available to everybody so everybody is aware of what can and should be done, and that would provide a better environment for everybody.
Have you had a chance to collaborate with universities and provide some of that education and provide that opportunity for university students?
I think we're all in our own ways working on different projects to do with universities,
Oh, okay.
right? I've got basically a year ago I gave all of my staff a mandate, that's the Canadian team, a mandate to reach out to the university they graduated at and maybe 1 or 2 others and go do like some form of course work, whether that's an evening intro to bulk material handling or a career fair or whatever,
Right.
like find someone at the university to start working with and get this stuff across. We visited a large number of universities.
Yeah.
Right. Understanding that really is the only opportunity they're going to have for that education.
It was really exciting to come speak here at University of Utah to all their senior students at a seminar. And there was an older gentleman in the back. He's like, I was here when Dr. Jenike published his work.
Oh, really?
And it was a game changer for the school.
Oh, awesome.
So that was very exciting. But we do try and get out to the universities. We already had 4 papers presented today. Education is a big part of it because it's flow is one thing, but it's also the loading, and that's a structural aspect of it. So silos fail. You can YouTube silos failing. And
Silos are the number one, or were, I haven't stayed up if it's true. I'm imagining it's still true, but certainly they were the number one failing type of structure in North America.
Oh, really?
Not too
I didn't
long
know that.
ago.
Oh, wow.
Yeah.
So we're trying
Lack
to
of understanding.
we're part of helping develop structural load codes as a Eurocode. We're on different committees to help make sure that these codes are being built
And through
correctly.
ASME also.
There you go.
And because the flow pattern that we're looking at before, funnel flow and mass flow and stable rat holes, etc., that flow pattern influences the loads, and then the loads need to be applied correctly to design the structure in terms of, okay, what's my plate thickness, what's my joint detail, things of that nature. So it's really you need to have that understanding of how the material flows through the vessel to calculate the loads to do the correct engineering design.
And that's at the design stage, right? And then there's also the usage, the maintenance, the management of change. A lot of times in the mining industry is not really different. If they have a silo, it's built. Imagine it's working reasonably well and everything's good. They kind of forget that it's an asset and it needs maintenance. It needs somebody to care for it, right? And if you say, oh, I want to go add a chute, there's one bin in particular that I'm thinking of. I went on site once and I was looking at this, and they decided that they wanted to add a chute. And so they took a chute from the vertical cylindrical wall of one silo, and they literally cut a hole in the silo that was right next to it, fed the chute through the silo, and cut a hole in the other side of the silo, out the other side, down, because the silo was in the way of where they wanted
Oh,
it to
no.
go. So they literally cut 2 holes and just shot the chute through, and
Yep.
then it went. And
Wow.
no one really understood the engineering impact of
Was the silo
what that
they
could
shot,
mean.
cut it through? Was that the one
Yeah.
that cut through still working?
Yeah.
It wasn't still.
Yeah. So imagine you've got 2 of these silos, and you want to shoot from one into the other. So they literally went from here through the other one and out down to their.
Just so you know, we do not recommend that.
No,
That is not a
That-
recommended
no.
solution.
Okay.
It's
well,
not
the
a
chute-
Jenike and Johanson design.
the problem, the chute worked,
The
meaning
shoot,
the
but
chute-
the one in between.
the material flowed through the chute from this silo to their
But
desired
the one in the
output.
middle had now a blockage.
But the chute now, in the center of the silo, had material flowing around it, and that poses a structural risk. Is
I'm
my
not an
point.
engineer by any stretch, and that does seem wrong. To
Yes,
me, that's
wrong.
wrong.
There's a structural risk there, and the point is that demonstrates the lack of attention that's being given to the silo that they put that chute
This
through.
is really random, but you know what that came to my mind when I don't know if you ever watched the movie The Apple Dumpling Gang. It's this old Disney movie.
Oh, maybe. I
These
don't
2
know.
guys are trying to rob a bank, and they've got this ladder, and they're trying to figure out how to get it through the building. They're running it through windows, and
I can
that's
see that.
same what I think.
Let's go there.
Yeah. And it didn't work out for them either. Okay, there's a couple things before I wrap up. Maybe we already covered it and I just sort of missed it. But the selective heat ore treatment, is that what we're talking about when you were talking about bringing a sample, and or did we miss that? Selective heat ore treatment.
We
Wait.
did miss that. We haven't
That's a
spoken about that.
technology.
It is a technology.
Yeah, I would like to. Okay. So that's an actual technology. Can we quickly touch on that before?
Yeah, exactly. So we're excited to kind of be part of that. We've been working on this for over a decade now with various groups. And at present, we have a partnership with Crescent Technologies. And the idea is that Crescent actually has microwave technology, solid state microwave technology that they're bringing to this. And from a comminution standpoint, and we know kind of, you take a rock, you've got to get the copper or gold out of this rock. So what do? We kind of hit it with steel balls and a rotating drum, et cetera, in the mill. And then it's very...
You're not going to pick on my beloved ball mills, right? I love those things.
Okay, I won't pick on it, but
Hitting a soft
just
spot here.
hear me out here for
Okay.
a second. So this is what we're doing in terms of technology. It uses a lot of energy, and the
Right. claim
claim is 3% or 4 or 5 or whatever percent of total world's energy
Right.
to grind down the rock to get the valuable mineral. So what we have in terms of the microwave technology, we're not going to get rid of your beloved ball mill, but if we put the microwave, say, upstream of that, we could pre-treat the ore before it goes
Oh.
into the mill. And then it has a number of benefits. One, it could reduce the overall strength of the ore.
So you're weakening the actual ore.
And then how we do
Right.
it, the microwave is it's like an impulse, kind of shock into the ore. And the microwave energy goes into the actual mineral, say the copper or the gold. It expands very rapidly, heats up, expands very rapidly, and cracks around the grain boundary.
Ah,
The
so
rock itself
there's a
doesn't
level of
heat much.
extraction.
And then, so you could imagine, okay, you're
Huh.
cracking around this grain boundary, and then you can better liberate then the mineral. So you take that, you pre-fracture, you get this weakened kind of grain boundary effect, then put it into the ball mill. You don't have to grind typically as fine, we're finding. You could float at a coarser particle size. And then also you can imagine too, if you open up these pathways in a rock, if you leach then you can get the liquid into the actual valuable mineral. You can leach that away. So
The access is better.
the access is better. So you can reduce the strength of the ore. You could float probably at a coarser particle size, or you could provide a pathway for leaching, all because of the differential heating between that valuable mineral, the copper, the gold, etc., and the gangue, which is transparent to microwave. It works best, to be honest, for a brittle type hard ore. And I think that's kind of where the benefit is, because obviously you're wasting a lot of energy, say in a SAG mill, a ball mill, HPGR, et cetera, if the ore is very hard. But again, if we can pre-treat that, soften the ore, get to that mineral a little bit more readily, that's where we feel that this technology has a big play in the industry.
This technology, sorry,
Yep,
this
no problem.
technology is out in the market. Where is it at in terms of?
We have gone through kind of the pilot scale kind of idea that's been proven, and at present we're kind of looking at the next scale up. So up to maybe 800 or so tons an hour in terms of throughput, although that could vary. So we've got anywhere between 10 tons an hour. We've got proposals out there at present for that, through to say 800 tons an hour in that sort of kind of tonnage rate. And you can put them side to side to kind of have larger tonnages as needed.
Well, I hope when that's like at full scale, you come back on the show, and that'd be great to unpack that for
Yeah,
sure.
that'd be good.
We definitely will very soon.
Yeah.
That's the plan.
Yes.
Then the other one I wanted to ask you about, David, was J-Purge.
Yeah, we've developed, this is going back a number of years ago. So for the plastics industry, polyethylene, polypropylene, the shampoo bottles are something that you have that you don't want the smell, you don't want the discoloration of the plastic.
Right.
So we've developed technology to purge gas through a gravity kind of discharging silo. So very similar mass flow silo. We'd inject nitrogen or steam into the silo, and that would permeate counter to the actual downward flowing material. So we kind of have technology where we can look at two-phase flow aspects. So fine materials, gas introduction, how does the material flow, how does the gas distribute? And then we can look at like pressure drops in the amount of gas to stop the reaction or purge the volatiles from the plastic. So the J-Purge technology is just exactly that, where we're injecting the gas in to stop that reaction or to actually purge the volatiles. And we've been doing this for many, many years.
Oh, okay.
Again, we can come up with the concept. We do the testing the same way. We do the conceptual design. We can do detailed design and fabricate the equipment. And in that particular case, typically the designs have inserts inside to kind of better improve flowability and also minimize grade changeover. Quite often in the plastics industry, you'll have like grade A will be processed and then want to put grade B kind of behind it. You want to minimize that grade changeover between grade A and B. And the insert design has the idea to minimize that grade changeover. And it also has the benefit of better introducing the gas to the actual column.
And this is integrated into a chute? Or
this is integrated into what we would call a bin or a silo. So
into the
it's
silo.
completely full of material here.
So you're integrating your technology into an existing silo, though, right? Is
Or
that
we
right?
can build a brand new silo, either or.
Oh, okay.
With it included.
With it.
Oh, I see. Oh, because are you actually manufacturing a silo, or you're working with a partner, or how does that work?
Maybe.
Maybe.
Sometimes we do the fabrication all
okay.
the way through, and sometimes we work with others who are doing it.
Oh, okay.
Exactly.
I wish I had more time to get into some of these topics because it. Okay, Carrie. Gen Zero is another, or Gen Zero is another topic that I had in my notes I wanted to cover, and again we're getting a little tight on time, so I wanted to get to it before we wrap.
Yes, just briefly, Gen Zero is a really innovative design for typically more for the biomass industry of feeding high material, the biomass material like chopped up wood or whatever it is, into a high pressure reactor. The current technologies available have significant risks that have actually shut down entire plants from succeeding. And so Gen Zero takes the knowledge of material flow and how to cross that pressure boundary. So we patented this technology of Gen Zero so that we can feed reliably well across these pressure boundaries. And that is a game changer for the biomass industry of this renewable energy. So we're very excited about that technology, and that's getting implemented. And we have bench scale tests, well, more than that, pilot scale of tests in California now. So you can actually run the material, see if it's a good candidate, how it's going to work, and then build and install the unit.
Just quickly, with some of this this development, is there a challenge in getting that out to the market? I mean, you said you did 4 presentations here. You're coming on this show, but it sounds like because you are applicable to a lot of different applications and processes. It must be a bit of a challenge sometimes to get the word out for them to integrate.
It is a challenge, and I think it's a challenge to get people to be the first ones.
Right.
And in the mining, it's always a kind of joke. Everyone wants to be the quickest to second, be the second one, the fastest second one.
I feel like that has shifted a little bit, though.
Yeah. And you know, hearing the presentations today and throughout, and companies saying, you know, we really appreciate people are willing to try what is right. Because the reasons that these technologies have come out is because there's been a major gap in the processing. And so we want to fill that gap based off our knowledge and help the industries actually improve.
Yeah, I was going to say a lot of these innovations that we're making are because there's been a problem that showed up and we wanted to fill it. So sometimes it's reasonably easy to get that into market.
Right.
But
because you're filling that gap that's has a demand. Yeah.
Yeah. But definitely it can be a challenge.
Yeah, I was just going to say that, though, a lot of our research work within the company is driven by client requests. So we've done this, and really from day one in terms of like mass flow, funnel flow, coming up with the test equipment, etc., and all these, the J-purge in terms of modeling two-phase flow and injecting gas into equipment. Really, a lot of our kind of technology that we have developed has been driven by kind of requests from clients. So we kind of like the questions, we like the difficult questions, we like the challenge. And I think that really drives the industry forward. It drives us forward, it drives the industry forward, because it's gone are the days we got asked, and I've been doing this 30 odd years, very simple questions, come up with a very
30 years, no way.
37. 37. But anyway, we won't go there. But
Sorry,
very simple questions. And as the year has gone on, we've been getting much more difficult questions. So, like there's multi-physics questions now in terms of, okay, the particles matter. Before we could just look at how material flows. What is the particle doing through the system? But now people want to look at too, how is the particle kind of reacting to? Is it going through a change? And the furnace question before, or comment before, we can test up to say 2000 degrees Fahrenheit or say 1000 degrees Celsius. But we can do that in a nitrogen blanket, so we don't have a reaction. But we could pump gas through the better material as we're doing the test. We've done direct reduction of iron ore, so you can do all these processes too, and it's all being driven by kind of other people asking questions. They're asking questions to us, and then combined, we're coming up with solutions. So it's quite exciting to be part of.
That actually leads me to my last question. And I was thinking even what we are as a production company. You end up. You start off with interviews. During COVID, it was a lot of remote interviews, but a lot of the events shut down, so then people gave us a try who normally wouldn't have tried working with us. But now we're moving more into on-site, but on-site means we're bringing in, like, you might want to get on someone else's site, and they've been on our show, so then we reach out to them. We can kind of coordinate it because there's trust there, and so there's this whole new set of challenges that we're going to be dealing with over the next couple of years, doing that more on-site production, which is a lot of safety concerns, and you've got cameras on oil and gas sites, mine sites. That's going to be a new thing for the industry. So that's a really motivating thing for me, because now it's going to be podcasts in mining were something different a few years ago. Now this on-site podcast is going to be even something different again. It's very motivating, and it's exciting for the team because we're all getting to do something new. What is that motivating factor individually as a company, whoever wants to take it?
That's actually something that when David was talking, I realized, like, you asked the question, is it hard to get technology out into the market? And I thought, you know what? We've done that. We've done that a whole bunch of times, like in a whole bunch of different ways. These ones that we're currently, trying to get out to market are just the newest ones. Other ones are sort of now, I would say, more or less accepted and kind of, the way that we do them and the way that in a lot of cases the industry does them. But yeah, like when we get a win and you finally get that first one in there, there's a big thrill there. That's actually, as an engineer, I think that's what drives me the most, is like when I'm on site and I see the bin that I helped to design. Yeah. Whatever stage I got to go to with the project, all the way through to fabrication of parts or anything like that, or just here's the concept and, go make it happen. But when I get to walk by it and see it there, I get like a big thrill out of having.
It doesn't go away.
Thrilling.
No,
it
doesn't.
Not. And I think that's why we retain our engineers for so long, is because we literally are making people's lives easier. We are making the world a better place. We are working on drugs and medications that are helping cancer patients, and they wouldn't have been to market as fast as it was if they had the flow issues. Yeah. So we're making a big change in the world, and that's very motivating. And I think we all love what we do, which is why we have the 90-year collective experience here.
And some of the mining problems have, in my view, some of the mining problems have like GDP level, impact. Yeah. Meaning those all did, like to David's point, if they all started up at nameplate capacity or better, on day one, the amount of
Right.
money that would equal for like the Canadian economy, for global economy in general, would be huge.
Yeah. Yeah.
Right. So the potential of the need is really there. And I think that really excites us.
And yeah, we really want to tackle those toughest, challenging problems in the world. We want to conquer that. So that drives us.
Well, from this interview, it seems like you're doing a pretty good job of it. And thank you for coming on the show. Thank you for kind of letting me kind of go take you off on different tangents. And that to me is the fun of the show.
Absolutely.
And I think it also shows competency as well. You know, anybody can read a script. Literally anybody can read a script. But to actually share and dig a little deeper, I think it's an important part of the show.
Absolutely.
Thank you.
Thank you so
for having
much.
us.
Thank you.
Cheers. Thanks for having us.
And thank you, everybody, for watching. We will have links to each of the guests if you want to connect with them on LinkedIn. Jenike and Johanson's website. I think that you have a YouTube. Do you have a YouTube channel?
Yes.
Yeah. Okay. YouTube channel, link to follow them on LinkedIn. And if you do not follow us, you just happen to, it came across in front of you, please hit subscribe to Mining Now. We will see you on the next episode.